So as I mentioned a minute or two ago, for whatever reason, even though the main refrain in that song is Teenage Wasteland, that's actually not the title of the song, although that's what everybody calls on their quest lines. The name of the song is actually Baba O'Reilly, which is not a phrase that's said at all in the song. Okay, so a couple announcements. Lab scheduling issues. I think there's a whopping 4 people out of the 300 and something that are registered for the 2 sections. There's all 4 that are currently not scheduled for your lab section. There are a couple lab sections that are open later in the day. Of course, the 8 a.m. one, which is always the most popular. So if you do want to switch into it, then feel free to do so through ISIS, obviously. I kind of lied. I said I'd have the clicker stuff ready today, and I didn't. So I'll have it by Friday, I hope. First homework is going to be out in 2 days. I will be going over it a bit on Friday. The material that we cover both today and during lecture on Friday is going to be largely what the homework is about. So I will be spending a bit of time talking about that homework both in lecture. We're going to go over an example that's somewhat similar. And then on Friday, I'm going to spend some time talking about the homework. Obviously, the second lab is tomorrow. As of earlier today, everybody who is registered for the course does have an account in the Olsen lab. If for whatever reason you did not receive an email, your spam filter ate it, your little sister deleted it, what have you, you can get your password reset tomorrow. The TAs will be able to reset that for you. But everybody should be able to log in with his or her own username rather than sort of the lab user that everybody was using. Right, and if you do have that email, print it out and bring it along. Questions, comments, concerns? Okay. So that, all right, this is a preview of the lab tomorrow. As it gets later in the semester, I'm going to spend a bit of time going over the labs. But the early labs are shorter and fairly self-guided, so I'm not going to spend too long talking about it. But generally, the lab is going to deal with, the idea for this class is that I go over something in lecture 1 week, the lab that week reinforces that, and the homework that is assigned that week uses that same material. Hopefully, we'll keep to that schedule, but this lab is going to go over a lot of the concepts that I'm talking about today, and we'll finish up on Friday, how to get input from the keyboard, which I'm going to kind of breeze over a bit, how to do computations, how to create variables, how to print stuff out. That's largely going to be what this lab talks about on Thursday, what we're going to see in lecture this week, and the homework that is due next week, we'll go over it as well. So that being said, that's the whopping preview I'm giving you of the lab. All right. So we were going through and we were talking about the basics of Java programming. We talked about variables, how to create variables. We talked about integer variables and double variables. Remember, an integer can hold any int, meaning 1, 2, 5, 15, -3, cannot hold a number that has a decimal point, such as 4.2. A floating point can hold a series of decimal points as well. And those are 2 different types of variables, if you will. They can hold specific values. Sure, you can stick 5 in both of them, but you can't stick 5.3 in both of them. And it turns out that there's a number of different types of variables that you can create, each which can hold different types of values. It's still some spot in memory that holds some value, but the particular type of value is different, and that's what the next couple slides are on. So it turns out that Java has 8 or so primitive types. These are called, we're going to see why they're called primitive types, but generally if I just say the word type, it's synonymous with primitive type. And there's 8 or so of them that we're going to be talking about today. It turns out there's sort of 1 or 2 more, but they're special types, and we'll see them later. There are 2 of them that are real numbers, meaning that they can hold something with a decimal point. Boolean is like Boolean algebra. It's either true or false, and those are the only 2 values it can hold. There's a character that can hold any character that you want. It can hold a Roman, from the Roman alphabet, A, B, C, D. It can hold kanji from Japanese or Chinese kanji. It can hold Korean characters. Obviously, we're going to be dealing, at least in this class, with just English-based characters. And then we have a series of types, 4 types, that are all integer types. They all can hold integer values, but they have different ranges. And I'm going to go over each of these types in a bit more detail in a minute or in the next couple slides. We're also going to see void. We're going to see this later in the semester. Void is means like nothing or null or empty. It's sort of a type. You will see it sometimes listed. We're going to be getting back to that a bit later in the semester. So a float takes up 4 bytes of space. So remember, a byte is 8 bits. So it takes up 32 bits of memory inside a computer. I'm not so worried that you remember beyond this slide and the next couple slides how much space a float takes up. It's important because I'm going to contrast it to a double. So I want you to understand that you don't have to memorize it takes up exactly 4 bytes. So a float takes up 4 bytes, and it has 6 decimal places of precision. Meaning if you were to write out pi as close as you could in a float, that's what it would look like, 3.14159. When we say 6 decimal places of precision, I mean that it can hold 6 digits in its number, and the decimal place floats among there. So it can hold 31.4159, 314.159, but about 6 places. Well, it turns out that that's not accurate enough for what a lot of times people want to do. So they created a type called the double. A double has been named because it is double the size of a float. So a float was named because the decimal point can float, meaning it can move back and forth. A double was so named because it is double the size of a float. So it takes up 8 bytes of space, or 64 bits of memory. And it turns out that it can hold about 15 places of accuracy, 3.141592653589979. So it can hold pi to more accuracy than a float can. This is why it's called double, just because it is double the size of a float, and particularly people who are creating it weren't all that creative in thinking of the names. This is very important. Always, always, always use doubles. You should never, ever, ever use floats. The reason is that Java sees a float and a double as distinctly different. And it will start giving you all of these warnings and start being really annoying and bark at your code if you start using floats. Everything in the Java library that we're going to see uses doubles. Therefore, if you start using floats, it's not going to work so well together. Computers can do a lot, but obviously it can't do conversion between doubles and floats very well. So as long as you always use doubles whenever you want some sort of real number, you'll be fine. So know that a float exists. Know that it's not quite as accurate as a double, but don't ever use it in this course. I mean, you're welcome to, but it will save you a huge headache. So those are the two, going back a slide, those are the two real types, which I will often refer to as floating point types, or floating point number. Again, unless specified otherwise, I'm always talking about doubles. So let's take a look at a byte. A byte has, by definition, 8 bits. And a bit can be either 0 or 1. Which means that if you have 8 bits in a byte, 1 byte can hold 2 to the 8th, or 256 possibilities in terms of how many values it can hold. Yes?
If everything in the Java library works better with double, then why do we still upload?
The question is, if everything in the Java library is doubles, why does Java still have floats? There are some cases when floats are better. In particular, if you are constrained in the amount of memory you want to use. If you have to store 1,000,000 values and you store it in doubles, it's going to take twice as much space as if you want to store 1,000,000 values and they're stored in floats. And if you don't care about the accuracy, then in that case, floats would be fine. We're not going to be doing anything that's going to take up a huge amount of memory in this course. So for us, the extra storage space that a double takes up is not really a concern. That's why one might use floats. But then you have to do sort of the special conversions between them, and that becomes a pain in the butt. So that's why they have it. But again, we don't really care too much about the amount of memory that a double versus a, let me phrase that. We're not too concerned with memory limits in terms of how much memory a double takes up versus a float takes up. Okay, so we have a byte. It's 256 possibilities. So any value that is stored in 8 bits can have one of 256 possible values. So it turns out that there's a Java byte type. It is an integer and can hold any one of 256 values. It happens to go between -128 and +127. When you include 0 in there, there's a total of 256 values that can hold. you cannot store, so if you create a variable of type byte, meaning, if I was to say byte B, I can't put 300 in it, because the highest value that it can store is 127. So, in C and C++, some of you may have seen it. There are unsigned versions of these, meaning numbers that are only 0 or positive. Java doesn't have that. So if you have seen unsigned in C and C++, that doesn't exist here. If you have not seen unsigned, then you can ignore that bullet point. So there are 4 integer types: byte, short, int, and long. And the difference is how much space they take up in memory, and therefore how many values they can hold. A byte has a total of 8 bits, so it can hold 2 to the 8th or 256 possible values. Negative 128 to positive 127. A short has 16 bits, so it can hold 2 to the 16th or 65,536 possible values, or negative 32768 to positive 32767. An int takes up 4 bytes, or 32 bits, so it can hold 2 to the 32 possible values, or about 4 billion. So you can hold negative 2 billion to positive 2 billion. A long takes up 8 bytes, 64 bits, and it goes to some really big number in the negative range, some really big number in the positive range. In general, we will mostly be using ints in this course. You should know, like floats, you should know the others, but unless specified, ints really, rarely are you going to need to store more than 2 billion. So it turns out, so we're getting near tax time, and a problem that, I'm sure a lot of us wish we had, is that the computers that the IRS uses to calculate your tax use 32-bit numbers. This becomes a problem for when you have greater than $2 billion as your asset, which I'm sure everybody here runs into that problem from time to time. Because the numbers, the maximum numbers, when your tax return is entered into the computer, because the computers cannot hold a value greater than 2 billion, it's using a 32-bit integer, then it can't compute your taxes. So they actually have special computers for the really rich people, the Bill Gateses and the Warren Buffetts of the world, that are reporting a heck of a lot more than $2 billion in terms of how much they're worth. But this is, actually, I remember reading an interview that Bill Gates was giving, which was a kind of dippy interview, but he was talking about how the IRS has to use special computers because he has so much money. So when you get rich, you also won't be able to have your tax computed on a 32-bit computer. I think TurboTax would also choke if you tried entering like $10 billion. Okay. So those are the types. We're going to see long a little bit later in the semester. I'm going to give a couple more examples of these. Long does appear from time to time, but generally we're going to be using ints. So we've seen many different operators. We've seen some operators. We're going to see some more. We have the normal addition, subtraction, multiplication, division. There's a couple special operators that that don't really exist necessarily in math. And one is plus plus, or increment. And what it does is it takes the value and it adds 1 to it. Minus minus takes a value and subtracts 1 to it. So if I was to say b plus plus, well, let's imagine that I actually stored a valid value in b, such as 3. So byte b equals 3. That creates a spot in memory called b and gives it the value 3. When I then call b plus plus as my next statement, that's going to take the 3 and just increment it to 4. All it does is add 1 to it. I can then do b minus minus, and then that's going to take the 4 and just make it a 3. In case you need a review of, adding 3 and 1. So consider this code. Int I equals 4, so that's going to define I, the spot in memory. It's going to give it the value 4. Plus plus I, I'm going to add 1 to it, and that I then becomes a 5. I print it out, and that prints out, not surprisingly, a 5. System.out.print line, and I'm going to print out the value in my variable. Now you'll notice that the next 2 lines are slightly different. One says plus plus I, and the other says I plus plus. They're actually called, the difference is this is called pre-increment, that's called post-increment. The thing is that when you're using this b plus plus or plus plus b or I or whatever it is, 2 things actually happen. First, the 2 things that happen are, one is added to the value, meaning it's incremented, and the other is the value is read so it can be used. When the plus plus is first, what it first does is it adds 1 to the value and then uses that value in the print statement. So we know at this point, after that line, it's 5. What this is going to do is it's going to add 1 to I, it's going to increment it, and then it's going to print it out. So this is going to print out 6, because it first added 1 to the value, and then it read that value that was in I and printed it out. This one does it in the reverse order. First it reads the value, 6, and prints that out, and then adds 1 to it. So what's happening here is you are actually printing out the old value. Because when that line completes, I is now 7, but it first reads the value and then increments it. So after that line is finished, I is equal to 7, but it printed out 6 again. And then that'll print out 7. So going back over that again, because it's an important concept, and I know this often throws people when they first see it. Whenever you have a plus plus I or an I plus plus, 2 things happen. One of them is that the value in that spot in memory is incremented by 1. The other is that that value is read to be used in the math equation, or in this case, the print statement. Which happens first depends on the order of the plus plus. If the plus plus is first, it adds 1 to it and then prints it out. If the plus plus is second, it prints it out and then adds 1 to it. Question?
What's the print ln and print?
Question was, what's the difference between print line or print ln and print? If I can hold off on that a little bit, I will talk about the difference between them. In fact, that probably should have been all print lines. The difference has to do with white space. I have a better slide that shows it, so I'm going to get back to that in a couple minutes. Yes?
Say for your second statement, if you did I plus plus, it's not printing it out. Is that going to make a difference? What do you do? Plus plus I plus plus?
No, that's a good question too. So here, all that is doing is just incrementing I, pre-incrementing as it happens to be. Because you're not actually reading the value for anything, you're not reading it to use an equation, you're not reading it to print it out. It doesn't matter if it's I plus plus or plus plus I, when it's all by itself. The time that it matters is when it's in a print statement. Because then you're either updating it and then reading it, as in that line, or reading it and then updating it, as in that line.
Does this only work for integer?
Yes. This is only for integer types. Byte, int, short, and long. And characters too, but we're not going to do it much with characters. But you can't do this with floats. You can't do this with booleans. Which are you supposed to use? The question is, which are you supposed to use? Either one. In most of the time that we're going to use this, it's going to be all by itself, such as that line. In that case, it doesn't matter which one you use. There will be, the reason I'm bringing this to you is when you see code that's listed in the textbook, they sometimes will use it in a case like this, and you should know the difference between it. If you're using it all by itself, when we get to for loops, for example, which is something we'll see in about a month, it doesn't really matter which one you use if it's all by itself. How many people feel they understand the difference between pre-increment and post-increment? Okay. How many people would like me to go over it again? Okay, I'm seeing some hands. So, and I do want to spend a good amount of time on this because I know this throws people quite often. Okay, int I equals 4, poof, we've created a variable, a spot in memory to hold an integer value. can hold negative 2 billion to positive 2 billion, we're giving it the value 4. And we're calling it I. What this does is this just adds 1 to it. So I then became 5. Here we're going to print it out, and it's just going to print out 5. So that so far is fairly straightforward. And it's the next two lines that start becoming confusing because of the order of what things happen. So remember that I plus plus and plus plus I, there's two things that they do. It first takes the variable and adds 1 to the value, making it 1 greater. So 5 will become 6, 6 will become 7, etc., etc. The other thing that it does is it reads the value in that variable to be used, in this case, in a print statement. And the question is, which order does it do it in? If the plus plus is first, then it's first going to add 1 to the value, 5 becomes 6, and then it's going to print out 6 to the screen. If the plus plus is second, it first reads the value, 6, and that's what will be printed out to the screen, but then it adds 1 to it. So at the end of that line, it printed out 6, but 7 is what was stored in the variable in memory. And that one just prints out the value, which is now 7. So I'm going to spend a bit of time coming back to this a bit later. I want to spend a lot of time to sort of introduce things, and I try coming back to it. So if it's not completely clear, we will spend a bit more time on it. Yes?
Would an additional plus add another 1 to the value, or would that do that in there?
Like plus plus I plus plus?
Yeah, or like plus 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 I.
You can't do plus 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 I. I think you can do plus plus I plus plus, but that's not considered good programming. Because usually there's plus plus I is used for some very specific things. If you're doing plus plus I plus plus, there's other ways to do it that is easier to read. You definitely can't do I plus plus plus. I guess you could do plus plus I plus plus. I don't know. I haven't tried it. Okay, other questions? Yes.
Not the second from the last line. Oh, basically, no, yeah. That line, basically, it should then add 1 and print at the same time, right?
Well, first what it does, that second to last line first prints out the value in I, and then it adds 1 to it. So this is going to print out the 6, which was in there, and then it adds 1 to it. So when that statement is done, 6 is printed out, 7 is stored in memory.
Oh, 7 stored in memory.
Right, and then 7 is printed on that line. Yes?
Did line 7 explain on the second line? If it's supposed to display.
You mean there? That is showing what I is at the end of that statement. So, yeah, I realize that's kind of confusing. What's here is not necessarily what's printed out. That's the spot in memory. So the variable in memory after the end of this yellow line is now 7. I should have interleaved the animations a bit better. So I've talked a bit about C and C++. C was around for a while, created in the early 1970s, and C++ came out in the mid-1980s. And the question is, of course, what were they going to call it? Because the precursor to C was B. So there was a couple debates. They thought maybe the successor to C would be D. Well, they decided to name it C++ because plus takes something and increments it, or makes it 1 better. So the idea there is that you're taking a language and you're incrementing it or making it 1 better. And this is why C++ is named C++. Sort of an inside joke that once you understand the post-increment operator, you sort of get what they're talking about. I didn't say it was necessarily a funny joke, but. Okay. We've seen 2 floating point types, float and double. We've seen 4 integer types, byte, short, int, long. There's 2 more left. We have a character type. A character is separated by or denoted by a single quote. If we're doing double quotes, that's a series of characters or a string. If we just have 1 character, if we just have 1 quote, then we're denoting a character. And as it turns out, every character has a numerical equivalent. Computers think in numbers. So if you tell it the character 0, or the character A, it's going to think the character A, or capital A, is number 65. And that's how it actually stores it in memory. If you tell it the character little a, it's going to store it as integer 97. The character 0 is 48, etc. There's a whole table called an ASCII table that lists what character maps to what number. You don't need to know that mapping. That's really not important because anybody can look it up. Understand that there is a mapping, and understand a couple other things about it that I'll get to, but you don't need to memorize that capital A is 65. Capital little a is 97. The interesting thing about this is after A obviously becomes B, then C, then D, then E, all the way up to Z. And while you may think that's kind of obvious, there were computers that had a non-continuous character set. It's much fun. So the point here is that the character B is equivalent to the character A plus 1. What you're saying is I'm going to take the character A, I'm going to add 1 to it, or move down 1, or move up 1 in the character set. So instead of A, I have B. Capital A plus 2 is going to be C. A plus 3 is D. And here note that this A and B is denoted by single quotes. So Java knows that you mean another character, just one greater. Again, we'll be getting back to this later in the semester. Last up is the Boolean type. There are all of 2 possible values for the Boolean type, true and false. You can't have anything in between. There's no fuzzy logic. There's no maybes, just true or false. And we have a bunch of Boolean-specific operators. How many people have seen Boolean logic before? Okay, some, but not all. We have the and, we have the or, and we have the not. I'm going to be explaining those operators in a bit more detail, I think in the next slide set, but at some point soon. So just like we have plus, minus, times, and divide, the operators that work on integer numbers and floating point numbers, we also have a series of operators for Boolean values as well. Okay. So it turns out that we need to declare all variables before use. Okay. Give me a second. So this is something that gave me apparently a bit of notoriety, but I mean, I didn't do this. I have some friends on the internet that just spontaneously mail me stuff, and some of it is actually appropriate to bring to class. So this is we saw carved watermelons. These are carved eggshells. And they actually took some sort of high-powered laser and carved these eggs, drained them somehow, and then carved them. And I think it's pretty amazing the texture that they got out of it. It is just the fact that the laser probably took, quite some time carving it. Somebody had to actually program the computer and the laser to do all that. So, yeah, somebody had lots of free time. Yeah, it's just a zoomed out version. So we're going to move that up there. Where were we? There we go. Okay. So turns out we need to declare our variables before use. And we talked about this briefly last time, in that if If you just say x equals 5, Java doesn't know what x is. Maybe it's a double. Maybe it's an int. Maybe it's a Boolean, and you can't do that because a Boolean can only have true or false. So any time that you want to store a value somewhere, specifically in a variable, you need to define that variable before you go and use that variable. So if you try doing this, Java's not going to like it. It's going to spit out a compile error saying, what does it say? Variable x is not declared or something similar. So you must declare or create a variable before it's actually used. Now consider this code. Int x, then system.out.println x. And notice here that we are now declaring x, but we're not giving it a value. Java, this is one of those things that I think, quite frankly, is very stupid about Java. They made a poor design decision, but, well, they certainly didn't consult me when they made Java. And, not surprisingly, I was younger than you when they made it. Int x creates the spot in memory, calls it x, but does not give it a value. When you see it denoted on the slides, it will just denote it as a dash. Yes, it could have given it a value of 0, or it could have given it a value of 1,000, or 1, or something like that. For whatever reason, Java does not give a variable a value unless you specifically tell it to. It calls it uninitialized because it hasn't been given an initial value. So if you try doing this, Java's going to sit there and say, I don't know what value x is. I'm not going to compile it for you. And it will actually choke on it and say, variable x might be uninitialized. So, oh good, I got the error message right. So in addition to the fact you must declare a variable before use, you must also give the variable a value before you start using it. Yes?
If you don't just, like, if you're not going to use x at all, you still, and it, like, I don't know, if for some reason it was initialized and you declared it and everything else, would it still get that message?
So the question is,
Like, if you had...
it has to do, right, yeah, I know exactly what you're asking. The question is, at what point would it give that message? Java, you can sit there and declare the variable int x and then do a whole bunch of other things that don't require x. Java gives this message. It will also give you a line number when you specifically try to use the variable that hasn't been initialized. So if you declare int x and then your whole program never uses it, Java's not going to care. It's not even going to tell you that that variable is unused. It will happily go and compile it. The only time it doesn't like it is when you try reading from it or reading the value in the variable when it has never been given a value. Then we have final int x equals 5. And notice now that we have the final keyword. This gives x a value. And the fact that it's final means that it can never be changed. This is a constant, a value that can never ever change throughout the course of your program. You can go and edit the file and say final int x equals 6, recompile it and rerun it, and that's fine. But you can never modify the value during the program. You can't later say in this program x equals 7 or x equals 20. Because it's final, Java will never allow you to change it. Hence why it's called final. It's a final value. So we're going to see a somewhat specific naming scheme for variables. This is discussed in the first homework, and I'm going to talk about it a bit both today and on Friday. But all constants need to look like this in terms of their naming scheme. All capitals with an underscore in between each word. There's a reason for this. There's a separate naming scheme for constants or final variables than there is for non-constant or regular variables. And this way, when you're looking at a program, you can easily tell what's a constant. Because if it's in all caps with underscores between the words, then great, you know it's a constant. So anytime that you create constants, and as we're going to see, we will need them for the first homework, they should always look like that. say int expression equals 4 plus 2 times 5. And like regular math, it's going to do the operations in a specific order. It first does multiplication and division from left to right, so it does the 2 times 5. And then it does addition and subtraction from left to right, so it's going to add 4 to that. So that will be 14 is the value stored in expression. We can then start playing around with it. Any time that we could otherwise put a variable, we can put an expression. We can say 5 over 2.0. That's going to print out 2.5. So each operator has a precedence level and associativity. I'm not really going to talk about associativity much in this class, but everything has a precedence level. The thing to remember is addition and subtraction is done after multiplication and division. So it does the higher precedence ones first, multiplication and division, and then the lower ones next. Associativity is how to handle ties. We have 3 times 2 divided by 4. Which one is done first? Well, most of the operators we're going to see are left associative, which means that you just go from left to right doing them in order. So 3 times 2 divided by 4, first it multiplies 3 times 2, and then it divides the result of that by 4. This is an important concern. When floating point is used, the result is a floating point. And I'm going to get back to that in a slide or two. So consider this. Knowing the rules of associativity, I think we can all look at that and agree that that does not really compute the average of A, B, and C. First, it's going to do the highest precedence stuff. It's going to divide C by 3, and then it's going to add A plus B plus 1/3 of C. Obviously, we can stick in parentheses and make this work right. But that, although a human looks at it and realizes what is meant, mostly because the variable name is average, a computer is not going to. So we have a slew of operators for int, right? The normal operators we've seen, plus, minus, divide, and time. It's also a percent sign. That's called modulus, and I'm going to show a couple examples of it. So first up, division. Division is integer division. What that means is there's no decimal point, there's no remainder. So 6 over 2 yields 3. You have an int on the left, you have an int on the right. And I mean on the left and the right of the division sign. So the result of that is an integer. 7 over 2 is also an integer. Yes, you and I know that in real life, you take 7, you divide it by 2, it's really 3.5. In Java, because both 7 and 2 are integers, the result is going to be an integer. It takes whatever is the left out of that and chops off the decimal place. So it doesn't round anything, it just forgets about the decimal place. So anytime you have an integer on both sides of the division sign, the result is the whole number of times that whatever is on the right goes into whatever is on the left. Modulus, that's the percent sign. And the problem is that we can now figure out how many times 2 goes into 7 evenly, but how many is left over when you divide 7 by 2. And that's what modulus tells us. Modulus gives us the remainder. Given a number, 7, and you want to find out if you divide 7 by 2, how many is left over, it's 1. Right? 2 goes into 7 3 times. 3 times 2 is 6. There's 1 left over. So anytime you see the percent sign, that's talking about modulus, and that's dealing with the remainder when you divide that by that. That's also going to be an int. 6 mod 2 is equal to 0. In particular, and this is going to pop up later in the semester, given any integer, if you mod it by 2 and it's 1, you know the integer is odd. And if you take any integer and you mod it by 2 and it's 0, you know the integer is even. Right? Because 2 goes into any even integer without a remainder, and 2 goes into any odd integer always with 1 remainder. So that we're going to see that that's an easy way to tell if the number's even or odd. Just mod it by 2 and check the remainder. And we'll see how to check the remainder in a bit. So floats and doubles, floating point numbers, real numbers, whatever you want to call them, they use the first four operators: plus, minus, division, and multiplication. In particular, if you take 7.0 and divide it by 2.0, the result is 3.5, which is what we'd expect. And then the question becomes, what happens if floating point numbers are mixed in with integer numbers? As it turns out, if one or the other of the operators, the operands, meaning the numbers, is a floating point number, then the result will be a floating point number. If and only if both are ints, then the result will be an int. So this is why 7.0 over 2.0 is 3.5. 7.0 over 2, well, at least one was a floating point, so it's going to be a floating point result. 7 over 2.0, again, at least one was a floating point, so it's a floating point result. 7 over 2, both were ints, result is also an int. So that's Java's rules, and the last bullet point on a slide or two before. If a floating point is in there somewhere, meaning either on the left or the right or both, then the result is a floating point. If neither are floating point, then it's going to be an int. So Booleans have a series of operators of their own. We have and, it's two ampersands. And essentially, if both of the operators are true, then the and is true. Now, I'm going to sort of breeze over this fairly quickly because the next slide set gets into ands and ors in more detail. So if I'm going over this too quickly, don't worry about it. I promise I'll get back to it. The vertical bars, two vertical bars, choosing the upper right keyword, that's or. If one or the other of the operands is true, then the result is true. And the bang, or the explanation point, is not. It basically converts. Like the negative sign to convert 3 to negative 3. Well, the bang converts true to false and false to true. So I'm going over these really briefly. I promise we'll see more examples of those either this week or next week. Okay. So I grew up in New York, and they have some really interesting ways of driving in New York, for those of you who have been there. And this is taken at one of the toll bridges. Now, at what point do you think they said, I should stop? And you notice it's not like when they first entered the toll booth, but they actually almost made it through. I know. Yeah, you notice the guy still trapped in his car. They're probably going to hook a tow truck up, pull them back out, or the ambulance can actually, the jaws of life will cut a car apart pretty easily.
Guess he's going to be late for work.
Yeah. This is where I learned to drive, so I suppose I can make fun of New Yorkers with impunity. So the print statement. As I mentioned before, you can print out many things with the plus operator. What that does is that takes all the things in the print line statement and prints them all out on the screen. So if I is 7, you said int I equals 7, semicolon. You can then say, quote, I equals, close quote, plus I. That's going to do two things. Java looks at this and says, this is a string. I know how to print out a string to the screen. 4 characters, I space equals space. It looks at this and says that this is a variable. I know what that variable is because it's been declared there. And I'm going to print out the value in that variable out to the screen. So that's going to print out I space equals space 7. There we go. I got it right. You can also have that statement on many different lines. Okay, or you can have a statement on many different lines, not that statement. It doesn't matter how many lines it's on. The only thing that matters is any string must begin and end on the same line. So I couldn't say, quote, hello, return, world, quote. But you can put it on many lines. And as we're going to see a bit later, we'll probably see it Friday, there are lots of reasons why you might want to do this. Right, you can't have a string on multiple lines. So that wouldn't be allowed. Yes?
So whatever you put in quotation marks, if you have a space in between those letters, Java will print it out just like that.
Exactly like that, yes. Anything you put in quotation marks, that exactly is printed out to the screen. The fact that there's a space here or here, that doesn't matter. But when Java sees a string, it assumes that that's exactly what you want to print out to the screen, and that's what it spits out.
You have multiple strings in one.
Sure. Yep. You can, as it turns out, you can put as much together as you want. You can say print line foo plus I plus bar plus etc. If you ignore my chicken scratches and imagine that you could actually read that, yeah. This is why I go on slides and don't write much on the board, because my handwriting is just horrible. So yes, Java will just take each of these and stick them all together and print out the entire thing.
Just on a side note, to make sure that I understand the quotation thing. So if I try putting plus and then in parentheses plus plus I, then it would print out I equals 8.
Hello world plus, like that? Yes. Because what that would do is, Java looks at that and would see that, let's change color. No. Yeah. First it's going to print out a string, then it's going to print out a number. And when it looks at the number, it first sees that there's a plus plus, so it takes I, changes it from 7 to 8, and that's going to print out hello world 8. I could do that, result in 3 over 5. That will print out result 0, or result colon space 0. Because remember, 3 over 5, that's integer division. The left and the right side are integers. 3/5 is about 0.6 on most days. 0.6 when you drop the decimal point is 0. So that's because it's just going to print out result colon space 0. I could do this. Results and 5 mod 3. So remember, mod is remainder. So it's going to divide 5 by 3. It goes in one time evenly with 2 left over. So that's going to print out result is 2. 3 over 5.0, because at least one of the operands is floating point, that's going to do integer division, and it's going to print out 0.6. 3 plus 4.0, it's going to take the 3, print out results 3, add that to 4, print out 7.0. Or not. As it turns out, the problem here, and this is actually what this was all leading to, the problem here is that the plus operator means a lot of different things in Java. It means integer addition. 3 plus 4 is 7. It means floating point addition. 3.0 plus 4.0 is 7.0. Although we look at those the same in a computer, they're actually done in completely different parts of the CPU. It also means take a bunch of strings and stick them together. When Java looks at all these other lines, it takes that string, or it converts that to 0. But it takes that and it takes that, sticks them together, and prints it out. Here, we're running into a problem that one of those pluses, we most likely mean take a string on the left and whatever's on the right and print it out. Right? That's what this plus here means. This other plus in there means add the two of them together. But Java doesn't know which is which, because the plus operator, as we're going to see, it's called overloaded. It has many different things that it can do. So what we want to do with this is put the 3 plus 4.0 in parentheses. Java will first execute what's in the parentheses, just like regular math. Puts them, adds them together, gets 7.0, because there's a floating point in there. And then it prints out result is 7.0.
Are
Question is, why don't you get closer on the numbers? We want Java, if we put quotes around the numbers like this, then it would print out results, space, 3% 5, or 5% 3. What we want to do is we want to take the numerical value that results from that operation and print that out. If we put quotes around it, it's just going to print out what the equation is. Right. I'll see you all on Friday.